Hello friends, let's begin our unit number 3. First we will see polymer compounding. It is the process of mixing or blending of polymers and additives. So you mix polymer and additive together, you get polymer compounding, and is essential for test trial. Typically this process is performed in the molten state with a goal to achieve homogeneous blend and is the crucial steps in the polymer development process. So let us see. Polymer compounding operation is very simple. Here the virgin palettes, okay, and then pigments and fillers and reinforcing agent. These are all compounding agent. Compounding agents are of various types: colors, fillers, pigments, okay, reinforcing agent, and then they are fed to the extruders. So basically they are using co-rotating and counter-rotating screws, then single screw extruder for all this processes of mixing, and then they throw it to pressure pumps, and finally they are cooled and then cut in the pelletizer, and then these compounded pellets are directly fed to the fabricator. And what does the fabricator do? It converts them into finished plastic products. So this figure 1.2 polymer compounding operation you should know. And let us see polymer compounding operation, what exactly happens there. The polymer compounding line shown is systematically in figure 1.2. Virgin pellets are converted to compounded pellets. That's the only thing that is happening. Virgin pellets getting converted to compounding pellets and then sent to the fabricator. Virgin pellets from the resin manufacturer are compounded with pigments, fillers or reinforcing agents at moderate or high concentration. Moderate to high concentration. The purpose of such operation is to improve the properties of the virgin based polymer or to give it specialized properties, adding value in every case. The production rates are in the range of 1000 to 10,000 pounds per hour. The processing equipment's critical task is to perform laminar distributive and dispersive mixing of the additives to the level required to obtain finished product property requirements. Furthermore, other additives such as chopped glass fiber are often fed after the compounding equipment has melted the pellets in order to minimize degrading the attributes of the additives. So if you don't want the additives attribute to be degraded, you have to add chopped glass fibers, okay, such as fiber length. Finally, to assist the laminar mixing process, the additives may be surface treated. The processing equipment used by polymer compounders is mainly co-rotating and counter-rotating screws. Then occasionally we also use single screw extruders in less demanding compounding line. As indicated in the figure 1.2, the same elementary steps of polymer processing described previously in post-reactor processing are performed by compounding equipment. So this is post-reactor polymer processing. This is the elementary step of polymer processing, where monomers, catalase, initiator, then polymerization reactor, separator, dryer, particulate polymer powder form, then we add them to additives. Additives are nothing but compounding, and then additives coated particulates, mixes, homogenizes, and co-rotating, counter-rotating screws, pumps, form, cut, cool in the pelletizer, virgin plastic pellets, shipped to fabricators and compounders. Okay. For further compounding, but this is also producing virgin plastic pellets. So what he's saying is that the same elementary steps of polymer processing described previously in post-reactor processing are performed by compounding equipment. So those same processes are repeated in the figure 1.2, which is of polymer compounding operations. So this PDF is quite long, you don't have to go through all of it, so you just read what is related to your syllabus. The compounded stream is typically fed into a multi-hole strand die, and the strands are first water cooled and then chopped to form pellets. The compounding operations exposes the reactor polymer to its second thermomechanical processing experience. The compounded product is shipped to fabricator of finished plastic products, commonly known as processes. So this is all regarding compounding. So now I will tell you what are the additives in compounding. Okay. So for that, let us go to the additives. So you have to remember all the various additives that are there in plastics. Okay. So let us see them one by one. It is very easy, you just have to understand what's happening. Addition of monomeric additive in compounding to produce the final commercial composition and properties is a very common and useful technique. At the same time, it should be recognized that such monomeric additive will often have lower chemical resistance than the polymer itself. In addition, each type of additive has certain important specific effects which should be considered. Now see plasticizer. What does the plasticizer do? The addition of monomeric liquid plasticizer to improve processability or flexibility of polymer is very common practice, especially in polyvinyl chloride and cellulose ester. These must be sufficiently similar to the polymer in polarity and hydrogen bonding to be miscible and compatible with it, and low enough in volatility and diffusibility to remain fairly permanently in it. So hydrogen bonding, it should be miscible, okay, and but it should also have low volatility and diffusibility to remain permanently in it. Okay, so it should be, plasticizer should be similar in polarity and hydrogen bonding so that it is miscible with it. Monomeric plasticizer are relatively non-volatile but still somewhat fugitive when heated or aged for long period of time. Most of them are less solvent and chemically resistant than the polymer to which they are added. Naturally, the polymer is much more stronger than them and which is much more chemically resistant, and many are extractable by soapy water, gasoline, motor oil, foods or dry cleaning solvents. Most of them are combustible and lower the flame resistance of the total composition. Naturally, if I add a substance which is weaker to a substance that is stronger, then the totality of the substance will decrease in its flame resistance, right? Also, many of them contain structurals which are less resistant to aging than the polymer to which they are added. And finally, some of them are fairly toxic and should be used with caution, where they could be extracted by food, drugs or cosmetics. So some plasticizers are toxic also. So if the use of the polymer is somewhere where there is food or cosmetics or drugs are there, then it should not be used. Okay, whenever there is consumption happening, so the material should not be toxic. Loss of plasticizer from plasticized polyvinyl chloride. So you see here, these are the plasticizer, di-2-ethyl-hexyl adipate. Percentage of plasticizer is 32. Activated carbon volatility is so and so. Oil extraction, hexane extraction 1%. So percent loss from 10 million flame. So because of this activated carbon volatility, oil extraction from 32%, 17.5% of this plasticizer is extracted like that. And this is the film of PVC, plasticized polyvinyl chloride. Now stabilizers. Substances which can help to stabilize the polymer against heat or ultraviolet degradation are extremely useful in many polymers. So systems that are very often added in small concentration for this purpose, their effect on electrical properties may be good or bad depending upon the specific stabilizer. For example, lead stabilizer in vinyl electrical insulation, although they are relatively polar, and ionic in nature actually improve the volume resistivity as resulting insulation, probably by absorbing ionic impurities which otherwise would have conducted electricity. Phenolic type antioxidants may stabilize the polymer against heat and yet be sensitive to ultraviolet light and thus synthesize the polymer toward UV light degradation. Such additives may also interfere with clarity. If they should happen to be incompatible with the polymer, some of them affect color, particularly certain UV stabilizers whose conjugated carbonyl structure may cause yellow discoloration. And carbon black, which is the strongest known UV light stabilizer, of course produces opaque black products in every case. In addition, certain stabilizers may introduce problems of toxicity. Lead, cadmium, and some tin compounds used to stabilize PVC are particularly important in this consideration. Cost of the thermal stabilizers is not usually a problem, but UV light stabilizers are extremely expensive and therefore used insufficiently in commercial practice. So these are the stabilizers for polymer. The structures are given, and UV light stabilizers are extremely expensive, whereas thermal stabilizers are usually not a problem. Reinforcement and fillers. Solid inorganic powdered fillers, just excuse me, help. Yeah. So solid inorganic powdered fillers are often added to increase rigidity and decrease cost. So why do we add solid inorganic powdered fillers? To increase the rigidity of the polymer and decrease its cost. And fibrous reinforcement are also added to increase strength and dimensional stability. Addition of fibrous reinforcing agents causes serious processability problems and increases processing costs considerably, particularly when long fibers, woven fabrics, and filaments winding techniques are used. Alkaline fillers tend to hurt electrical properties. Clay fillers may actually improve volume resistivity radically. For example, vinyl electrical insulation. This is probably due to their ability to absorb ionic impurities which otherwise would have been mobile enough to conduct current. Carbon black, graphite, copper, and other metal fillers can actually be used in high concentration to produce electrical conductivity. In addition, most reinforcement and fillers have refractive indices different enough from the polymer to make it quite opaque, and many of them may introduce colors or at least tinting effects. Now, cross-linking agent. The use of curing agents for thermosetting resins, cross-linking agents for some thermoplastic resins, and vulcanizing agents for elastomers is very important for their final mechanical, thermal, and chemical properties, and depends upon a delicate balance between pot life versus the rate and extent of cure. Curing means making the polymer more hard, means it is having cross-link. All the chains are cross-linked, then there is a dense structure, less volume, polymer becomes more hard. They must be carefully chosen to optimize this balance. Most of them cause opacity and some of them cause color. In addition, some of them are toxic and must be avoided in applications where they would be detrimental. Foaming agents. The use of foaming agents which decompose to liberate nitrogen gas is very important in the production of some types of foams. These are quite expensive and some of them also produce toxic byproducts which must be avoided in certain applications. Very toxic foaming agents cannot even be tolerated in normal processing techniques and require particularly good ventilation. So foaming agent is basically used when you need to make sofas of polyurethane. So you need foam. Foam is a soft, light rubber material that is used inside seats and cushions. Now, flame retardants. Nobody wants their polymer to be inflammable, so flame retardants are added. Organic phosphates and halogen compounds, often synergized by antimony oxide, used together with antimony oxide, are frequently added to polymers to increase their flame resistance. At the same time, these additives may lower thermal and ultraviolet light stability, particularly if they use organic halogen compounds. Many flame retardants cause opacity or toxicity problems as well as and most recent increased cost. Lubricants. Lubricants are often added to improve processability and to reduce friction in the final product. They may be liquid or low melting waxes which exude to the surface, in which case they may produce poor surface appearance or cause painting problems. Or they may be solid like MOS2 or brass dispersed throughout the polymer, in which case they cause opacity and sometimes loss of strength. So if you want to increase the processability and reduce the friction in the final product, you have to add lubricants. Now, antistatics. Ionic materials such as quaternary ammonium compounds or hydrophilic materials like hydrophilic material means water loving materials such as polyethoxylated organics are often coated on finished products or added to the polymer composition during processing to reduce its tendency to develop and hold a static electric charge during processing or use. So, if you don't want the static electric charge to be produced during processing, you have to add anti-static agent. Those which are simply post-coated on the surface are impermanent. So if you simply coat the anti-statics over the polymer, it will be impermanent. It will not be permanent. Those which are added during compounding and processing must have precisely the right amount of semi-compatibility so that they will continue to migrate to the surface and replace the superficial material which has worn away during handling, and neither the mechanism nor the technology of their action handling and use neither the mechanism nor the technology of their action is well understood. In addition, some of the best anti-static quaternary ammonium compound have less than sufficient thermal stability and tend to decompose to volatile tertiary amines and produce very undesirable fishy odors during high temperature processing. Biocides. The addition of biocides to protect the polymer against bacteria, fungus, rot, and rodents must not simultaneously produce serious toxicity to humans either during processing or during long-term use. This requires a very delicate balance of toxic properties, which is often hard to achieve. Ideally, they should be semi-compatible and migrate gradually to the surface during use so that they may continue to replenish the surface layer which is being worn away by use and handling, so that they may continue to replenish the surface layer which is being worn away by handling and use. Some of them harm the color stability of the polymer, particularly during thermal processing. Many of them are expensive as well. Use of elements or groups such as lead, phenols, aromatic hydrocarbons, and aromatic amines introduces problems of toxicity to humans, which must be considered and guarded very carefully. Colors. The addition of colors to polymers is a fine art of blending and color matching. For maximum thermal stability, inorganic colors are generally used, and since these are generally incompatible with the organic polymer, they produce only opaque colors. Development of clear, thermally stable organic colors is much more difficult. Certain colors, such as cadmium compound, introduces the problem of toxicity. Many colors break down chemically, particularly during thermal processing or ultraviolet light aging, causing discoloration in use. So this is all regarding the additives and plastics. So read it, you'll understand there's nothing difficult in it. Now let us see the elementary ideas of processing. The historical evolution of polymer processing. So in the year 1850 to 1950, rubber and plastic technology focus product machine invention scale product machine activity industry entrepreneurial discipline incentive inventive praxis and technology inventors benefit new class of material new industry. Then as the time passed, 1950 to 2000, process and machine design, product machine, corporate lab, academy, industry, transport phenomena, rheology, computational field mechanics, profession, chem, ME, chem, ability to process very diverse polymers, large resin and processing industries. Transition, process design and design products, products micro structuring, product micro structure, academic, corporate labs, advanced compounders, transport phenomena, full rheology, melt solid physics, interfacial phenomena, polymer chemistry, inline characterization, thermodynamics, value added materials, new application fields, customized structure and properties. Future, macromolecular engineering, new products and structure, pushing the limits, product molecular microstructure, government, education, collaboration, high-tech startups, new industries. So now you can see the activity is quite increased. Truly advanced polymer material, new generation of globally applicable polymers. So the elementary steps in processing, you have to remember something. The analysis of polymer processing in terms of elementary steps and shaping method. The field of polymer processing has been traditionally and consistently analyzed in terms of the prevailing processing methods, that is extrusion, injection molding, blow molding, calendering, mixing and dispersion, rotational molding and so on. So these are the various processing methods which are already established, and some of them we have in our lab also, and if you visit any industry you will see them. So number one is extrusion molding, then injection molding, then third one is blow molding, then fourth one is calendering, fifth one is mixing and dispersion, sixth one is rotational molding. So these six you should at least remember. In analogy to chemical engineering, these processes have been viewed as unit operation of polymer processing. At the time of writing of the first edition of the text, when polymer processing was maturing into a well-defined and well-studied engineering discipline, we found it necessary to re-examine this classic way of analyzing the field, because the manner in which a field is broken down into its component elements has profound educational implications. A careful worked out analysis should evolve into an abstract structure of the field that accomplishes the following objective. So this is basically all theory, you don't have to remember that, but you do have to remember the six processing methods. Focuses attention on underlying engineering and scientific principles, which are also the basis of the unifying element to all process. Helps develop creative engineering thinking, leading to a new, improved design. Provides an overall view of the field, facilitating quick and easy assimilation of new information. Focuses attention on underlying engineering and specific principles, which are also the basis of unifying element to all processes. A quarter of a century later, and in retrospect is talking about the past events, right? The analysis that we presented then and that we discussed later help fulfill the previously defined objectives and move the field forward. The shaping steps. The first step we take in analysis of polymer processing is to clearly define its objective. In this case, the objective is undoubtedly shaping polymer products. The shaping operation can be preceded and followed by many manipulations of the polymer to prepare for its shaping, modify its properties, and improve its appearance. Nevertheless, the essence of polymer processing remains the shaping operation. The selection of the shaping method is dictated by product geometries, and sometimes, when alternative shaping methods are available, by economic consideration. Reviewing the various shaping methods practiced in the industry, we can classify them in the following groups: calendering and coating, die forming, mold coating, molding and casting, stretch shaping. The first shaping method is steady continuous process. It is among the oldest method and is used extensively in rubber and plastic industries. It includes classic calendering as well as various continuous coating operations such as knife and roll coating. Now, die forming, which is perhaps the most important industrial shaping operation, includes all possible shaping operation that consists of forcing a melt through a die. Among these are fiber spinning, film and sheet forming, pipe, tube and profile forming, and wire and cable coating. This is also a steady continuous process in contrast to the last three shaping methods, which are cyclic. The term mold coating is assigned to shaping the methods such as dip coating, slush molding, powder coating, and rotational molding. All these involve the formation of a relatively thick coating on either the inner and the outer metal surface of the mold. The next method is molding and casting, which comprises all the different ways of stuffing molds with thermoplastics or thermosetting polymers. These include the most widely used shaping operation of injection molding, transfer molding, and compression molding, as well as ordinary casting of monomers or low molecular weight products in situ polymerization. Finally, stretch shaping, as implied by the name, involves shaping or preformed polymers by stretching. Thermoforming, blow molding, stretch blow molding, and cold forming can be classified as secondary shaping operation. The first three are very widely used. So, in blow molding, what happens? You have this small polymer coming out of the machine, and then air is filled in that polymer, and that air enlarges the polymer like a balloon, and when it get expanded, to control its expansion there is a shape of a bottle given, and when it cannot expand further because of the shape of the bottle, the polymer acquires the shape of that bottle, and that's how blow molding is done. You can see the videos on YouTube of blow molding. You will clearly understand what I'm talking about. The Plasto company has this blow molding by which they make water tanks. The complex rheological properties of polymer melts play a dominant role in shaping operations. Thus, introduction of one of the most striking aspects of non-Newtonian behavior, that of shearing thinning pseudoplasticity, has been successfully incorporated into the analysis of melt flow inside polymer processing. Similarly, by applying the modern sophisticated tools of numerical method, the incorporation of the elastic nature of the polymer is being carried out with increasing success, particularly in stretch shaping. As mentioned earlier, during shaping and post-shaping operation, a good deal of structuring, that is, retain macromolecular orientation and specific morphologies, and is being imparted to the final plastic product. Structuring has long been understood to be very significant technological importance. The detailed understanding of structuring requires the ability of quantitatively describe the flow of rheologically complex melts, heat transfer, nucleation, and crystallization under stress. Work in this area is now underway as we discuss in the last section of the chapter. The elementary steps. The polymer is usually supplied to the processor in particulate form. Shaping of the polymer takes place only subsequent to a series of preparatory operations. The nature of those operations determine to a large extent the shape, size, complexity, choice, and cost of the processing machinery, and significance of a thorough understanding of this operation cannot be overemphasized. One or most such operation can be found in all the existing machinery, and we refer them as elementary steps of polymer processing. So, what are the elementary steps of polymer processing? There are 5 clearly identifiable elementary steps. Number 1, handling of particulate solids, then melting, then pressurizing and pumping, then mixing, and finally devolatilization and stripping. So, defining handling of particulate solid as an elementary step is justified considerable the unique properties exhibited by a particulate solid system. Subjects such as particulate packing, agglomeration, consolidation, gravitational flow, arcing, compaction in hoppers, and mechanically induced flow must be well understood to ensure sound engineering design of processing machines and processing plant. Subsequently to an operation involving solid handling, the polymer must be melted or heat softened prior to shaping. Obviously, if it is melted, then only it will go inside the die. Often this is the slowest and hence rate determining step in polymer processing. Severe limitations are imposed on attainable melting rates by the thermal and physical properties of the polymer. In particular, the low thermal conductivity and thermal degradation. The former limits the rate of heat transfer because low thermal conductivity, so rate of heat transfer will be affected, and the latter places rather low upper bounds on the temperature and time the polymer can be exposed, because otherwise it will get thermally degraded. On the other hand, beneficial to increase the rate of melting is the very high polymer melt viscosity, which renders dominant the role in viscous energy dissipation. Plastic energy dissipation arising from compressive and shear deformation of compound of polymer solids particulates in twin rotor equipment. In such a powerful heat source, it may result in nearly instant melting. All these factors emphasize the need to find the best geometrical configuration for obtaining the highest possible rates of melting and for determining the processing equipment needed for rapid and efficient melting. Now the molten polymer must be pumped and pressured must be generated to bring about shaping, for example flow through dies or into molds. This elementary step is called pumping or pressurization. Pressurization and pumping is completely dominated by the rheological properties of polymer which melts and profoundly affect the physical design of processing machinery. Pressurization and melting may be simultaneous and the two processes are to interact with each other. Moreover, at the same time the polymer melt is mixed by the prevailing laminar flow, mixing the melt distributively to obtain uniform melt temperature, uniform composition. Working the polymer for improving properties and a broad range of mixing operations involving dispersive mixing of incompatible polymer, breaks up of agglomerates and fillers. All these belong to the elementary steps of mixing. The last elementary step of devolatilization and stripping is of particular importance to post-reactor compounding, blending, and reactive processing operation. Although it also occurs in commonly used process, for example, devolatilization invented two-stage SSE, single screw extruder. This elementary steps involve mass transfer phenomenon, the detailed mechanism of which have been investigated in some depth since publication of the first edition of this book, and yet therefore unlike in the first edition, here we devote full chapter to this step, yet more research is needed to fully elucidate this complex process. The theoretical analysis of processing in terms of elementary steps, which considers the basic physical principle and mechanism involved in each elementary step, has been helpful since its introduction in gaining better insight into the currently used processing methods, encouraging further work on their mathematical formulation, and perhaps also stimulating creative engineering thinking on improved processing method. It has helped provide answers not only to how a certain product works, but to why a product is made a certain way, and foremost why a particular machine configuration is the best or the appropriate one to use. The latter question is indeed the essence of engineering. For these reasons, we will maintain and add to this approach in this edition. So now these are the 4 elementary steps of processing. So you remember them, and what are they? You try to write it down in 3-4 lines. That is enough. So this PDF is very big, you have to make it short, but the elementary ideas of processing, these 5 ones you need to know.